Hello everyone. Today we would like to continue talking about how we can design our groundwater model. This is part 3 of this topic, and in this session we are going to learn more about the boundary conditions.
Same as previous video, many of the pictures, plots, tables that you will see in this presentations are coming from the Spoke Applied Groundwater Modeling written by Mary Anderson and William Wisner.
Okay, in previous sessions we learned that groundwater flow can be modeled using different forms of the groundwater flow governing equations, which is in the form of partial differential equations, right? So we said that to solve this problem, we need to have boundary conditions or initial condition information, and we can go and numerically solve for the h. So the solution of this equation is the h at each x, y, z, and t domain. So MODFLOW is the most well-known numerical model which can go and solve this equation for us and find the head at each position x, y, z, and t. But MODFLOW, as again we'll talk more in detail, MODFLOW is a block-centered finite difference model. So it is a finite difference based model, and the nodes that you'll see, for example, it means that actually the system will be discretized into cubic small cubes like this, and the node of each block is exactly at the center of the cell. Okay, so the head will be assigned to this point. So technically we have the x, y, z information of this node, and as you know, maybe sometimes I see that some people get confused. So technically each cell, so this is the governing equation for each cell. So we go and solve this equation for in the entire space domain of the system. So models can be MODFLOW 88. MODFLOW for the first time was developed in 88 and get better and better next years, and the last version of MODFLOW, which is I think released in 2017, is MODFLOW 6. What is the difference between these? Technically, the later ones have some sort of advantages, so they have more features. For example, they can go and make a better estimation of recharge for each cells, and they may work with different packages, and sometimes calibration. Some of them works better in calibration, and there are minor differences between these, but what they do, they go and solve this equation for us. So MODFLOW USGS is a groundwater model, which it's a very interesting model which can consider non-cubic form of the cells that we are going to talk about. For example, if we have an area like this, it can go and use different forms of block system rather than cubic system. And again, as you know, there are two forms of finite difference and finite element approaches to go and solve the governing equation for us. Finite difference is a much more standard method, and it is free and everyone can go and download, but finite element solves or reaches better solutions, not in all cases, in some cases, but as far as I know, you have to pay and actually get this. But we are going, again, as I said, we're going to talk about these details later. Again, we learned that we have three mathematical forms to represent our boundary condition. We call them type 1, type 2, and type 3 boundary conditions. For the specified head boundary condition, which is the type 1, technically we assign the value of head to each nodes, which is at the center of the cell. For the specified flow boundary condition, technically these boundary condition is assigned to the surface, or I would say to the volume of the cell. And if you remember, once we derive the governing equation, we said that we can do a mass balance inflow minus outflow calculation, and we said that we may have a recharge sink and source term, which would be applied to the surface, or like a well, what you see here, we can inject water into the system. So the W term was associated with the volume of water which comes from out of the system, or the volume of water which we take out of the system. And it is a pretty similar concept that you'll see in next slides, and you'll get familiar with. And the head dependent boundary condition type 3, again, technically we calculate the Q or flux information, and we apply it to the phases or the volume of the system, and the computer or the numerical model like MODFLOW goes and solve for H and assign this H to the associated node. Using a specified head boundary condition, modeler forces the system or the model to have specific head value at any specific nodes within the system. It doesn't matter, it can this node can be within the system or at the perimeter of the system. The thing is that just the modeler says that I know how the head changes at this specific location. That might be a constant value for the entire time domain of the system, or the modeler can say that, well, I know how the head at this system changes with time. For example, at time 0 the head was 10 meters, but it goes up, it comes back, and do something like this, whatever, but I know how it changes. Okay, there is a well-known package, we call it time variant specified head package, which beautifully goes and takes care of this. And you can go, and the modeler can go and define how the head changes at different times. But as we discussed again earlier, we said that we should be very careful with assigning this form of boundary condition, because we force the system to have a specific value, which at some situation it might be problematic. This system, the specified head boundary condition or the CHD package, usually get used to simulate rivers, lake, reservoirs, ocean, which we know that the value of the head, for example, if there is a stream like this here, and if we know that the groundwater gets into the system, into the river, we know that the river is big enough, or the contribution of the groundwater is small enough not to change the stage in the river. That would be lake, that would be ocean, right? So this system is this form of a specified head boundary condition suits better for features which we know that the groundwater stresses will not change their hydraulic head values. As we said, the specified head boundary condition suits to model the rivers, streams, lakes, surface water bodies like this, but usually we use this form of boundary condition, a specified head boundary condition, to represent the surface water bodies when the surface water body like this stream that you see here is well connected with the entire assigned cell. Okay, so it means that, for example, it is deep enough, or the hydraulic conductivity of the river is huge enough to say that the head at this specific point under the river is, for example, is the same as the stage of this river. So this is for some sort of, so this is something that modeler needs to decide, but usually we consider the specified head boundary condition for a fully penetrated wells or well hydraulically connected system. But for the partially penetrating system, for example, if we have a shallow stream or our cells are too big, we can go and use, you'll see that actually it is better to go and use the head dependent boundary condition, the type 3 forms of the boundary condition, to go and take care of the boundary condition in these areas. The type 2 boundary conditions, which is known as a specified flow boundary condition, again similar to the specified head. Now this time the flux at any phase, or at the volume of at any phase, the flux at any wave phase, or the amount of water changing at the volume of the cell is known. Okay, so the same as, for example, same as this, pretty much like the specified head, the modeler would say that, well, I know at this specific surface of the cell, I know how flux changes with time. For example, the flux goes up, the flux goes down, but whatever it is, I know how it changes, and I force the system to consider this amount of W or R at that specific location. So lateral faces technically takes care of the horizontal flow, or the exchange of water horizontally. Top and bottom faces, if they have a specific flux, they take actually they take care of the vertical flow. You'll see actually next slides we're going to talk more about these, but specified flow boundary condition can also be used to assign a sink and source term within the system, which is nothing but the pumping or injecting well. For example, for pumping, we know that a specific amount of water gets out of the cell per unit time, or the injection actually the other way, we know how much water gets into the system per unit time. And using these, we can go and represent different hydrologic processes or hydraulic processes within our model that we're going to practice in next slides. Groundwater modelers use specified head and specified flow boundary conditions a lot in their models, but it is very important to know that technically most of the hydraulic processes or hydrological processes that we concern in groundwater modeling can be simulated using both specified head or specified flow boundary conditions. But we usually prefer to consider and define boundary conditions using specified flow concept rather than a specified head concept. So the one reason is that, so as you saw earlier, the one reason is that we usually use the specified flow boundary condition once our, for example, if this is our, I don't know if this is, so if these are my groundwater cells, for example, that actually I use, so I can consider specified flow boundary conditions in condition like this when the system is, the stream is well connected with the aquifer, and I can assume that the head at that node changes pretty much like how the stage of water changes. If this goes up, this goes up. If it gets down, this gets down. Okay, so for example, that was one limitation. The other important limitation was that we said that the value of the head at the node is independent of amount of flux which would get into the system. Okay, because we force the groundwater to go and always keep or change the head at this specific node as modeler likes. This is the other limitations, and we know that usually the specified flow type boundary condition can represent the processes much better than the specified head boundary conditions. That actually you will see. So because in specified head, in specified flow condition, we calculate the flux and we let the model to go and update the value of the head at that point rather than we forcing it. Okay, and there are some researchers and some very experienced groundwater modelers. They say that a specified flow boundary conditions works much more better or improve the calibration processes that we're going to briefly talk about in next slides. But calibration is something that we usually use in our groundwater models, and they say that the specified flow boundary condition works better with the calibration processes rather than specified head. The no flow boundary condition, which you hear a lot in groundwater modeling world, is a specific form of the specified flow boundary condition, but we assume that the flux at that specific phase is 0. Okay, which it means that actually the gradient at that location is 0. It is very important to know that by default, the groundwater model assumes that, for example, if you have a system like this, and if you discretize the system into multiple cells, and if you forget, for example, to assign any specific boundary condition here, by default, the groundwater model puts no flow boundary conditions at the perimeter. So at the very beginning, all of these are no flow boundary conditions, and if the modeler wants to change the boundary condition, for example, make it a specified head boundary condition, it needs to go and assign the boundary condition here. Head-dependent boundary condition is the third form of the boundary condition, which we use a lot directly or indirectly in so many packages. And technically what happens here, using this boundary condition, we first, the code calculates the flow across the faces that we are concerned, or we would like to define a boundary condition. For example, if for example, think about this face. Okay, so the model goes, or the package goes and calculates the flux at this face, and the MODFLOW goes based on this flux, goes and calculate the head at that node. In previous sessions I gave you this example. I said that if this is our model, if this is the lake, and we would like to know how this lake contributes to the model, we said that we can go and define a head-dependent boundary or HDP boundary condition, for example, here. So it is similar to this. So this is for if this is the lake and if this is the face of the system that we would like to go and find the amount of flux at that point. Technically, we can go and use the Darcy's law. So herein, I can go and find the Q if I know this length, if I know the length here, and if I know the cross section here, which I know, and I know how the head changes here and here. So the head, HIJK, is the head exactly at that cell. Okay, IJK, actually we use this to address the specific cell. HB is the hydraulic head, for example, at the lake, and the C is the conductance, which can be calculated as this formula. Head-dependent boundary condition can be considered for both horizontal or vertical flows. This was an example of the horizontal flow, but as we already discussed, we can use this form of boundary condition to represent the not fully penetrated streams or not well hydraulically connected system. For example, if these are my cells, and if I know that the stream is disconnected, I can go and define a code, or I use a package which can go and calculate these Q rates, which gets applied on top of these cells. I can use these Q's and convert these Q's to the W term that we had in the governing equation. If you remember, that was the second. Remember? So it was W SS partial H partial T, right? So the code can go, the package can go and calculate the Q here, and once I have the Q, it can go and convert it to the W and put it in this equation and MODFLOW and pass it to MODFLOW, and MODFLOW goes and solve for the head at these cells. So technically now we give flexibility to these nodes to get updated based on the situation, based on the hydraulic processes. So we use HDP head-dependent boundary condition concept a lot in groundwater modeling, because they can go and represent different vertical flows. For example, the interaction between the aquifer and streams, the aquifer and lake, wetlands, drains. Evapotranspiration is something that we can use this boundary condition to simulate, and also the lateral or bottom boundary flows in our model. For example, our system, for example, if this is my groundwater, I know that if this is, for example, if this is a cell which represents the, I don't know, for example, a confining or clay system like this, and I have another aquifer here, and I want to model, and there's another clay layer here, which I want, there's another aquifer here, and I know that, for example, I have the value how this Q would change based on the head calculated in these cells. So then I can go and consider this form of HDB conditions to model these two layers and include the interaction of this aquifer here under the system. So I just wanted to show you that we need to be careful and think about the underlying layer of underlying face of bottom face of the model as well. So, and again, for the horizontal flow interaction, we had an example of a lake which was outside, and we would like to consider how this lake would contribute to the system horizontally. Let me erase these. So how we technically again calculate this head-dependent boundary condition, we use this formula, the very basic Darcy's law-based formula, which we have a C term, conduction term here, and we calculate, the model calculates the head at the cell, and we somehow, the modeler gives the HB information or the head varying information. For example, the stage, this hedge would be the stage of the lake. The modeler gives this information, or there are even some more complex system which goes and calculates these heads for us, considering the contribution of the groundwater to the system and other hydrological, or for example evapotranspiration or inflow outflow. So this HB can be given by modeler or can be calculated in the complex system, but Hij(k) is the value of the head at the cell. And we have different packages which use the HDB concept. So river package is something that we're going to talk about in the next slide. So these are the important and well-known packages. The river package, which takes care of the rivers, the streams, drains, takes care of the drainages, evapotranspiration, general head boundary condition, and lake packages. So these are, and also well packages. So these are the packages that we are going to talk about and learn more how we can use these, or what hydrological processes these packages can represent. So you may wonder what the term package means, that I use a lot in this video, and I'm sure that you've already heard this. The packages are like the subroutine that we had for or we created for our main code. For example, here in the main code is the MODFLOW, which can go and solve the partial differential equation, find the H information for us. But these packages are developed by different people, and they went and created, for example, a well package which can go and simulate the well and provides the information which the MODFLOW needs, and helps us to better simulate the impacts of well. The other packages, for example, the river, as you can guess, can be used to simulate rivers, streams. There are so many different packages: evapotranspiration, drain package, time variance specified head. We already talked about this. So if you want to learn more about these, you can go and find the documentations for each of these packages and go and learn and understand how they work. But we usually based on the conceptual model that we have, we look at our conceptual model. For example, if there are cells which we need to consider evapotranspiration, we check this package, or we want to activate this package, or if we have well, we go and activate the proper either MNW1, 2, or MNWI. We select each and use them to produce required information for our MODFLOW. Okay, let's start with a river package. In the river package, for example, if these are my cells, groundwater cells, and if for example there is a river here, so technically this package goes and so let me if this is, for example, if this is the riverbed, so the model goes and calculates how the water can go and pass through this riverbed and gets recharged into these cells under the river. So this package goes and use this information, which is this formula, which Kz is nothing but the hydraulic conductivity of the bed. So technically it goes and solves exactly this problem that we had in our homework. Okay, so it goes and solves, and this is the portal system, and there is a head here. So the head here is the stage of the river. So this is the riverbed, and the head here changes at each delta t, and the computer goes and calculates what is the value of this. So knowing this, knowing the head here, and hydraulic property of this, I can go and calculate the flux, the Q at that phase, and eventually turn it to the W term. Okay, so they use the similar formula. This is the thickness of the aquifer. This is the head of the cell, which I calculate, and the HS is the head of the river. But sometimes I see that some people get confused, but you need to know and pay attention to the fact that we are talking about groundwater models. So we don't care, or let's say this, whatever you may see in the surface of your model, in your conceptual model, we actually don't have them in our groundwater models. What we do, for example, a stream. So we don't have a stream in our groundwater models, or lake. So we just think about the cells which are buried under the ground. So this is a groundwater system. What we can consider is that we can go and consider how the river can contribute, or the lake can contribute to our system, and we simulate the impacts of that surface water bodies into our groundwater. Okay, so this is something that you need to be careful. We are not going to design or model the surface water bodies here. So how this river calculates the W term? For example, if you look at this, technically we go and map our rivers, which came from the conceptual model. For example, suppose that actually this is a discretized area, and these solid lines are my river. So I have one river here, the other river here, which gets into they merge and creates this river. So I have the location of these rivers. Again, I'm not modeling them. So this is just a conceptual model, and this conceptual model just gives me this information that I need to consider the impact of river in this cell, 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 and so on. Okay, so this is the only thing which this conceptual model gives me. Okay, so I can go and find the cells which I need to go and consider the river impacts on them. Okay, so what the package, the river package does, river package goes, and it's so many GUIs or river package goes somehow ask these information, or itself goes and calculate these information for you. For example, based on your conceptual model, it goes and find the length of the river within that cell. For example, here it is this much. For this cell, it is smaller, and it is this one. So it goes and calculate the length of the river, which you see here, for example, in this picture. Okay, so in this picture, it goes and calculates the L for you, or it asks you to put. I mean, I think that in many nowadays system, it automatically goes and calculate the length based on the conceptual model that you've created. It asks for the thickness of the aquifer. So it asks you to input this information. That would be different for each cell, or it would be constant for the entire system. So this is the extra information that we need to provide. And also the width of the stream is again something that we need to give. For example, we give a W term here. So having the L thickness and W, I can go and calculate the Q, right? So this was the C, the similar formula, okay, which C itself is a function of K and thickness and area. Okay, so these are the information which I need to provide to my conceptual model, and the river package simplifies the system. So this is a very good picture actually. If this is my river, I know that this is the river. For example, if my cell, for example, if I have one cell here, okay, exactly under this bed, so under this river. So technically what happens, it goes and simulates or simplify the system into this form. In this form, you see that actually you have a beautiful cubic river. Okay, so everything is rectangular. This is the river bed, and I assume that there is no the sides or the banks of the river are impermeable, so the water cannot. So I neglect the horizontal interaction at these spaces, and I go and calculate the Q and then W term for this specific cell. So using river package, we can go and simulate the interaction between the stream and the aquifer in three forms of interactions that we already talked about. These two, the gaining and losing streams, are pretty much a typical groundwater interaction, but sometimes we have disconnected stream, and this is a very rare situation, but sometimes it happens. So as we said, in a cell, for example, if this is a cell, we have head here, so that would be our head, Hij, okay, so it has a value, and actually its value is the same as this amount. Okay, so this is the head
at the cell in the groundwater. On top of that, the head of the stream is this much. As you see, the head of the aquifer in this case is higher than the head of the stream, so technically it means that the water goes from the river, from the aquifer into the river. So the system can go and use this formula to find the amount of water which leaves the cell into the stream. So if we have the hydraulic conductivity, the thickness LW, which is the area, we can go and calculate the Q and then convert the Q into the W or R term. In next slide, I'm going to show you how this river package can take care of this specific disconnected stream form. Okay, in the disconnected river, technically the head of the cell, for example, if this is our groundwater cell, for example, the head at the cell is way below the bottom of the riverbed. So the bottom of the riverbed is a number which is given by the modeler. So the model can go and compare if the head is below the S spot, then it assumes that the system is disconnected. And the disconnected system is pretty much like an example problem that we had in the homework. So if this is my column, if this is my water storage, technically this is the stream. This is the stream stage. This is the river bed. And here in this case, we assume that the water drips from the bottom. It means that it is in the atmospheric pressure. So it assumes that the air bubbles are here, and actually we have an atmospheric pressure situation. So technically it goes and calculates the amount of Q. If you want to write the Darcy's law, you'll see that actually you will eventually lead into this equation. So you go and calculate the amount of water which drips actually from the riverbed, and assumes that it eventually goes and reach the groundwater table. There are other packages which take care of the interaction between the stream and groundwater, other than river package that we talked about. Their names, they are actually categorized under stream packages. So there are multiple forms: SFR1, SFR2, and STR packages. The main difference between the stream package and river package is that in the river package, we assume that the interaction of the amount of water which, for example, gets into the stream is negligible, and the stage level is independent of amount of water which is being given to the aquifer or taking from the aquifer. Technically, the stage information, the HS information, is actually an input value which a modeler inputs into the model. Okay, but stream package is an advanced and a little bit complex package, which itself goes and does some hydraulics calculation. For example, it uses Manning's equation, and it flood routes and finds the HS value. For example, in the hydraulics class, we've learned that actually how we can go and find the depth of the shallow surface water flows, right? So there are some equations like Manning's equations that actually these packages use to go and calculate HS for us. So in these systems, there are much more processes which are considered like the inflow, outflow, evapotranspiration, and so on. But as you see, you're making your system, your model complex. Accordingly, you need to have more data like the slope of the river channel, the hydraulic radius, and the property of the and form of the channel, and Manning's parameter. So this is the main difference between the river and stage package. The stream packages. Again, as we already discussed, you know that you can model or simulate streams using the specified head package as well, but we usually try to avoid for the reasons that we already talked about, and we better simulate them using river package or stream packages rather than considering it as a specified head condition.
Okay, lakes are the other hydrological elements that we usually want to consider in our groundwater modeling. So there are multiple ways to go and simulate the impacts of lakes on our aquifers. One is to use specified head package. So this is pretty much like the river package. So lake packages or lake concept is very similar to the river discussion that we had. So if we assume that our lake is well connected with the system, or it is fully penetrated, then I can go and say that actually the head at the lake is exactly or pretty much like the stage level. So I can use the CHD package, or I can use a general head boundary condition. The general head boundary condition is exactly like the river package, so it uses the QHS minus HIJK formula to calculate the K and eventually transform it into the W4. So the difference is that if I want to draw okay, for example, if this is my lake and if this is my river, for example, let me connect it to this. So if this is my river, I know that I need to go and find W, which comes from the lake in this cell here, 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 and I need to consider the river impacts in this here, 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 here. Okay, so but if you remember, to find the conductance of the river, we said that the model goes and finds, we have to give it, or there are tools which can go and calculate the LS for us. We need to give the W term. So having L and W, I can go and find A. If I have the thickness and K, I can go and calculate C. Okay, but here in the lake, it is a little bit different. I need to give this area information. Again, it can be given manually, or there are tools which goes and automatically calculates this area based on your map, drawing, or conceptual model that you had. So you have your A calculated like this, and then you go on. Again, pretty much the same idea. If the head at the cell at the groundwater is higher than the lake, then it is the lake which gives water to the system, or the other way. And also you can consider a disconnected lake as well. But again, I hope that you are not confused with this diagram. You need to think about it. If it is not clear, you need to read more and make sure that you understand the situation. So technically, this might not be intuitive. Technically, if in the nature, if I see a river which flows, technically the groundwater head, if I put a piezometer into the river, if I go and read the head under the river, I might get surprised that the head at the river, at the aquifer, in the what I see in the piezometer, is below the stream level. So if I want to let's draw it this way. So if this is the water moves like this, okay, so this is my stream, and if I go and put a piezometer and actually drive a piezometer into the riverbed, I would see that actually the head might be lower than the stage. So it means that the river gives water, or it may be even higher. Okay, it means that actually, so there are two heads here. So one head is the head of the stage. So I want to say that there are two heads here. This is the head of the river, or stage of the river, which we are not modeling, and the head of the aquifer. Okay, so that was the second approach, but the third approach is using lake packages. So if I want to, you remember that actually there was a difference between the river packages and stream packages, right? The stream packages, they went and used the Manning's equation. It was much more complex to calculate the HS, the head of the stream. Similarly, the GHP package, we have a GHP package for the lake, and also we had the lake packages. Okay, lake packages are like stream packages. They consider much more advanced processes. They, for example, they consider the lake bed sediments, hydraulic property, water budgets, inflow, outflow, recharge, evapotranspiration, and so on. So it is a much more complex form of the GHP, which simulates more hydrological processes. But these were the three techniques or packages that we can use to go and simulate a lake's impacts on our groundwaters. This is another diagram which shows how we simulate lakes. For example, if this is my lake, we already talked about this, that technically we are not modeling the lakes, right? So what we have the aquifer cells like this, and we want to find the W terms here, in some cases even horizontally, if our lake package can handle that. Okay, so as you see, it is pretty much like the river package discussion. Okay, wells are next hydraulics processes that we want to talk about. As you know, pumping and injections are the main ways of getting or putting water into the groundwater system. And well packages are designed and developed to take care of this process for us. Technically, what happens here is that I want you to learn actually how, if you know how these processes are modeled in packages, then you can go and based upon the conditions and situations that you will be in, decide how to use or manipulate these boundary conditions. But wells, if are considered as a sink and sorter within each cell. For For example, if you look at this cell, so they assume that the well is screened in this cell, and it gets Q amount of water at specific time, so they have the flow rate here. So they know how much water is getting out of the volume of this cell per unit time. And it goes and manipulate and change it and turn it into a W term. Okay, that's simple. So technically, to the W, if you look at your notes, you see that the W is the volumetric inflow rate. So this is the amount of water which gets into or out of the system, out of the volume of the cell per unit time. So this formula. So if you have Q, you can go and convert the Q information into a W information and put it here and solve your problems. And in GUIs, for example, in GMS, there are some interfaces that you can go and say that, for example, I have 3 wells. One is in cell 1613, the other one is here, the other one is here, 3 cells, and these are the flow rates. Okay, and again, if you look at the sign, we already talked about this, that the positive W means injection. And it is very important. If you make a mistake here, so technically, which happens a lot actually, I've seen a lot that people are making this small mistakes. And the negative is pumping. Okay, and it is simple. If you get confused with this signs, you can think about this way. So you can assume that these are all 0, and you have just W term, right? So W is SS partial H partial T. So if you add, if your W is positive, it means that your heads goes up. Okay, this has to be positive. So this has to be positive. It means that HT plus delta T minus HT over delta T should be positive. To be positive, the head at T plus delta T should be higher, right? So it means that injection is should be considered as positive, and the other way, negative, means that actually this goes down. Okay, but be careful with the sign of this pumping and injection well. So, but this was pretty much the basics and fundamental concepts of the well. So technically, we consider that how much Q is getting out of the volume of the aquifer or volume of the cell, and calculates and pass it to the MODFLOW, and it goes and solve this information for us. But in next slide, you'll see that we have other well packages for other situations. As you saw in previous slide, we assumed that if we have a well, we assume that it is fully penetrated here, or even if it is not fully penetrated here. For the penetration, I mean the screen, the well screen. For example, in reality, the well screen would be something like this, right? But I assume that it is like this and uniformly extracts water from the volume everywhere into the system. So this is the equivalent form of the system. But my screen, for example, if I have another cell here, my well screen would be extended into the lower cell. Okay, so in this situation, there are some different packages which they go and calculate. So I have two cells. I need to find the W term here, W1 and W2, okay? And I have one Q, right? So there are different packages, and based on their assumptions, they go and distribute the Q into Q1 and Q2, okay? And similarly, they go and find W1 and W2. For example, they say that the one way is that, and also you manually can do this. You can go and based on the transmissivity of this cell and this cell, so this might be T1, this might be T2. So they may have different material. So based on the transmissivity of each cell, you can go and find, say that for example, if the transmissivity of this higher than this one, it goes and actually goes and calculate or distribute cells here, or there are other ways. For example, in MNW2 package, it goes and uses the Tim's equation, and which you've learned in which you can go and look at the textbook and see and learn what is Tim equation. But they use this equation and somehow distributes the Q and W into multiple sets. So, but these are the multi-node well packages that we usually use. And if you want to learn more, you can go and read the documentations and how exactly learn how these models work. For example, in some packages, they decrease the vertical hydraulic conductivity as well to let the system gets water kind of horizontally from the sides, which is much more realistic. So there are so many different assumptions, but the main idea is that it goes and distributes the Q information and W information for each node or cell. And I put this reference here. That would be one of the best references. If you want to, you can go and learn more about these well packages. But the important thing is that you need to know that these are the point information, which will be calculated based upon the Q, and it will turn into the W information. There are a few things that it's worth mention here. One is that we have different forms of wells. We have domestic wells, industrial, irrigation, and municipal water production wells. And also in engineering system, we have dewatering. We have wells that we use for dewatering the tunnels or mines. But depending on the Q value and the extraction value of each well, it doesn't matter. It is a pumping or injection well. Depending based on the value of Q, we may go if our model is too big and there are some wells, for example here, which has a very small amount of Q, we may go and ignore these wells within this big, huge model. So the size matters here and the Q matters here, that you need to go and think. Sometimes there are some wells, for example, the domestic wells, they don't extract a lot of water, so we assume that they don't have any direct impact on the groundwater situation in the region. It is good to know that we usually assume that the wells are vertical, but in some cases, for example, in engineering problems, the wells can be inclined or horizontal, and actually we can go and model these. And also, if our cell sizes are too big and there are two wells, for example, in one cell, we usually there are different approaches. We need to avoid the situation and rearrange the cells to see that to have at least both one well in each cell. Or if we can't, technically what we do, we go and consider both wells at a time, and we add the flow rates. Again, as you may remember, we already talked about this. If this is my system, and if I have wells like this, and if this is my discretized system, technically now I consider this well to get a specific amount of water from the entire cell, as we discussed. But if I'm interested to know exactly what is going on around the well, so it is better I use a different coordinate system, like use a radial coordinate system or radial governing equations, or I need to zoom in and use much more smaller size cells around the wells. And we are going to talk about this. There are some packages that they use we use to refine the cell sizes. But if you want to get a better result around a well, and if it is important to you, you need to go and use a very smaller cells. Okay, I want to stop here, and next session I'm going to talk about the aerial form of the boundary conditions. So all of these were kind of a point-based boundary conditions, but next sessions I'm going to talk about the aerial boundary conditions, and I want to finish this video by showing you this very beautiful painting. Thank you.